This video is an introduction to confidence intervals. So here's a setup for our very first example. Imagine a school district is trying to improve student scores on like a statewide biology test. Okay, so imagine, if you're familiar with North Carolina schools, the EOC classes, at the end of a lot of high school courses. Let's assume that in this district for a long time, the average score on the statewide test has been about 70% in this biology course, and the scores are normally distributed. This is often true for test scores. And let's say the standard deviation across students is 15. So the district is trying to improve the scores. It makes some pedagogical changes to the course, and maybe they're not completely confident that it's going to be successful. So they do a pilot program. They pick some students, hopefully randomly, and maybe there's 4 classes with 85 students total. And after trying out the new way of teaching the class, the average test score for those students is 75. All right. So here's the setup. What we're trying to learn about is an unknown population parameter of interest. It's the mean score across the whole district if the new program, if the new way of teaching the course was adopted. So we may feel that we know the old mean is 70, but we don't know the new mean. All right. We don't know what would happen if these changes were rolled out to the entire district. So mu is the new mean score, and we don't know what it is. What we have is an estimate from our pilot program. The mean score among those students is 75%. Is this point estimate precise or reliable? In the sense that, as the number of students taking the new version of the course increases, will their scores be really close to 75, or could it move around a lot? And so far, we don't know the answer to this. This is what we're trying to address in this topic. So you can think of confidence intervals and the next topic, hypothesis tests, as ways that are trying to provide information about this, about the sort of reliability of our estimates, to give us a sense of how much our estimates might be contaminated by sampling variability, and ultimately trying to answer questions like, if I see a mean of 75 among these 85 students, should I treat that 75 as meaningfully different from the old average of 70 or not, right? And in order to say something about that, we need a sense of the amount of sampling variability, okay? All right, we're going to start with the simplest case, and that requires making some strong and unrealistic assumptions that we'll drop as soon as possible, okay? And those 2 assumptions are the population follows a normal distribution, and we know the population's standard deviation. So in the test score example, I picked that example because it's a case where it's plausible, at least, that the distribution of student scores is normal. And I conjectured that we know sigma is 15. Maybe the standard deviation under the old program was 15, and we're willing to assume that that's still going to be the standard deviation under the new version of the course. All right. The known sigma in particular is not a very plausible assumption in almost any situation, right? Because we're trying to learn about the population mean. How would we know other features of the population, like the standard deviation, if we don't even know the mean, okay? So we'll relax this assumption soon, but we're going to go for it, go with it for now. In this case, the sample mean is normally distributed for any sample size, all right? We don't have to appeal to the central limit theorem here. The sample mean, if the population itself is normal, then the sample mean will also be normally distributed for any sample size, okay? Remember, it's unbiased, mean mu, and its standard deviation is sigma over square root of n. So if we standardize that, then we have a standard normal distribution that we're familiar with. And you may remember that if you take a symmetric interval around 0 for the standard normal, minus 1.96 to positive 1.96 for the z-scores, that puts almost exactly 95% of the area under the standard normal curve, okay? And we can use that to construct a confidence interval or interval estimator for the population mean. And I went through the math here. I just start by repeating this statement here, and then we're going to drop in our definition of z here. The standardized version of x bar follows the z distribution. And then we'll just do some algebra on this, move the sigma over root n to the outsides here by multiplying through. And then we have this minus mu here, and I want to get rid of the minus sign. Remember, if you multiply through an inequality by a negative value, so in this case -1 is what we're going to do, you have to switch the sign on the inequality. But I'm also, as I do that, I'm going to swap what's listed on the left and the right, okay, which is all kind of happening at once in this last step. But what we get down here is we have mu in the middle, and then we have x bar minus what we're going to call a margin of error, and then we have x bar plus a margin of error. And that margin of error is that 1.96 times the standard deviation of x bar. Okay, this is a weird probability statement because the random thing is x bar, and it's here at sort of the edges of the statement. And then there's this fixed parameter value mu that's in the middle. All right, but this says the probability that this interval, x bar minus margin of error, x bar plus margin of error, the probability that that interval will contain mu is 0.95. All right, so this is a random interval. This is just a different way of writing the interval. This is the lower bound. This is the upper bound. Typically, I will write it more compactly as x bar plus or minus the margin of error. Okay, and again, the important thing to remember here is when you think about a confidence level or probability 0.95, that's something that applies across possible samples. So some confidence intervals, most confidence intervals will contain the true parameter value, and some will not, okay? And that's across possible samples. This, I've already used this term margin of error. It's the half width of the confidence interval. Right here is the definition, okay? So it's the center of the confidence interval is the estimate, and then you go minus one margin of error to get to the lower bound, and plus a margin of error to get to the upper bound. We've used a 0.95 or 95% confidence level, right? That's here. Generally, we express the confidence level as 1 minus alpha is the notation that's used for that. So the alpha value there is 0.05. And if you look at the table here, so this is a standard normal curve. We've picked a symmetric interval around 0 that puts probability 0.95 or 1 minus alpha in the middle of the distribution, which means there's alpha over 2 probability in the right tail and alpha over 2 probability in the left tail. In this case, what we've been working with, 2.5% in each tail. Okay, and the value on the horizontal axis here that makes that true is 1.96. Okay, this is known as a critical value. All right, a critical value. These are positive by definition. So there's the critical value here, 1.96, and there's the negative counterpart of it over here, minus 1.96. Right? And if you wanted a different confidence level, just pick a different critical value. So if you're willing to accept a lower confidence level, all right, you can get, you'll have a smaller confidence interval because you only need to put 90% in the middle here, which means you can pick a critical value that's sort of closer to 0. Right? And if you want a higher confidence level, you have to accept a wider interval that goes with a higher critical value. So a 99% in the middle here, confidence level, would put just 0.5% in each tail, and you'd really have to sort of push these critical values out to the edges of the graph in order to do that. Okay. I'll just say one more thing, which is just to emphasize this idea of a random interval. Okay. So you've seen in class when we talked about the z-distribution, so we have, in a lot of these problems, we're thinking of the z as coming from like a standardized version of something that's normally distributed. In this case, sample mean, x bar. All right, so if we think about drawing sample mean from a population with mean mu, and we know that under random sampling, this thing is unbiased. So on average, our estimate will be mu, but some estimates will be too high, some estimates will be too low. Okay. Then that critical value is set such that we have like mu plus 1 margin of error over here, and we have mu minus a margin of error over here. All right. And then imagine, so this will just keep track of the value mu, which will then sort of map to a z-score of 0. All right. And what we're saying with this idea of a random interval that has a certain probability of covering mu is that a lot of the time we'll get an estimate that's like close enough So there's our confidence interval. And, even if our estimate is, let's say, a little further off here, that's fine. Okay. These estimates will generate confidence intervals that include mu. Same with this one. Okay. But just by the sort of properties of the sampling distribution, occasionally you will get an estimate that is sort of further out in the tail of the sampling distribution, out here, beyond the critical value. And then that confidence interval won't include mu, all right? That's like a failed confidence interval. That's a miss, okay? Most of the time, your interval will include mu, right? But just by the nature of the method, you have to accept that that probability won't be 1. It's not going to happen all the time. Some confidence intervals will be a miss, okay? And again, that's being driven by the random sampling. So across possible samples, you expect a certain share of samples. Most of them will generate estimates that you can construct a confidence interval around, and it contains mu, but some of those estimates will be sort of outliers, and the confidence interval will not cover the parameter value.